Cosmology can reconstruct nearly the entire history of the universe, yet the earliest moment remains beyond observation. For more than a century, this field has operated under a central assumption: that the past, if it left measurable evidence behind, can be reconstructed. Modern cosmology does not rely on belief or speculation. It relies on physical signals that still exist today: light, radiation, particle distributions, and large-scale structure. Records that carry information about conditions that no longer exist, yet remain encoded in measurable form. From this foundation, modern cosmology has achieved something extraordinary. It has traced the universe backward through billions of years of expansion. It has identified when atoms first formed, when light first traveled freely, when matter began to cluster into the earliest large-scale structures. These reconstructions are not speculative narratives. They are constrained by observation, cross-checked by independent measurements, and refined through decades of increasingly precise data. This success has created a quiet expectation that the universe, no matter how old or extreme its earliest phases may have been, is ultimately observable in principle. That even if we cannot yet see the very beginning, it remains something that better instruments, longer observations, or more advanced techniques could eventually reveal. But that expectation is false, not because of technical limitations, not because of incomplete data, and not because of missing ingenuity. The failure is deeper than that. It is structural. Every line of evidence we possess, every measurement that allows us to reconstruct cosmic history, points toward a boundary, a real boundary, a point beyond which no signal can reach us, no matter how long we wait or how advanced our technology becomes. This boundary is not defined by human capability. It is defined by the physical conditions of the early universe itself. To understand why this matters, it is important to be clear about what cosmology actually observes. We do not observe the past directly. We observe information that has survived. Light emitted long ago. Radiation released under specific conditions. Patterns frozen into matter distributions that persist as the universe expands. These signals move forward through time, carrying with them a record of the state of the universe when they were produced. As long as signals can travel, the past remains accessible. But there exists a point in cosmic history where this condition fails. Before that point, the universe was not transparent to information. Signals could not propagate freely. Radiation could not travel long distances. Any information about earlier conditions was erased almost immediately by the surrounding environment. Not hidden, not distorted, eliminated. What remains observable today is therefore not the full history of the universe, but the earliest moment at which information was able to survive long enough to reach us. This distinction is subtle, but it is fundamental. When cosmologists say they are studying the early universe, they are not referring to the beginning in an absolute sense. They are referring to the earliest accessible phase, defined not by time alone, but by the possibility of observation. This is the point where our evidence begins. Everything before it is not simply unknown. It is unobservable in principle. This creates a paradox at the heart of modern cosmology. We possess a detailed, quantitative account of nearly everything that happened after a certain moment. We can describe conditions with remarkable precision. We can test predictions against observation. We can refine parameters and reduce uncertainty. Yet the closer we trace the universe back toward its origin, the more sharply we encounter a limit that no improvement can overcome. The paradox is not that we do not yet know what happened at the beginning. The paradox is that the beginning may be something we can never know through observation at all. This is difficult to accept because it conflicts with how scientific progress usually unfolds. In most areas of science, unknowns are treated as temporary. Gaps in understanding signal future work. Better data resolves ambiguity. Improved tools extend reach. History suggests that boundaries retreat as knowledge advances. But in cosmology, one boundary does not retreat. It remains fixed, not because we have failed to cross it, but because nothing from beyond it can cross to us. Every improvement in observational precision reinforces this conclusion. The better our measurements become, the more sharply this limit is defined. Far from dissolving, it becomes clearer. This creates a shift in the nature of the central question. The question is no longer simply what happened at the beginning of the universe. It becomes, why does observation itself fail at a specific point? And why must it fail regardless of future progress? Answering that question requires re-examining what is meant by evidence, by observation, and by reconstruction in a universe whose earliest conditions were radically different from those we experience now. It also requires letting go of a comforting assumption that every event in the universe leaves behind a trace that can be recovered. Some events do not. Some conditions erase their own history. The existence of such a boundary does not diminish the achievements of cosmology. On the contrary, it emerges directly from them. It is precisely because the universe has been studied so thoroughly and with such consistency across independent methods that this limit can be identified with confidence. The unsettling realization is that completeness does not imply total access. The universe has a history. We can reconstruct much of it, but the existence of a history does not guarantee that all of it can be observed. This is where the journey begins, not with a lack of knowledge, but with a recognition of where knowledge necessarily ends. To move forward from here, it becomes necessary to redefine what it means to observe the universe at all, not as a passive act of looking backward in time, but as a process constrained by the physical conditions that allow information to survive. Only then can the boundary itself be understood, not as an obstacle to overcome, but as a feature that shapes everything we are able to know. And it is this redefinition of observation, rather than any single event at the beginning, that will determine how far cosmology can go. If the beginning of the universe cannot be seen, the question immediately becomes more precise. What does it actually mean to observe the universe at all? The paradox, introduced earlier, does not arise from ignorance. It arises from the way cosmology gathers knowledge. To understand why observation reaches a limit, it is first necessary to clarify what observation means in this context. Cosmology does not function like direct observation in everyday experience. No one is watching the past unfold. No instrument is pointed backward in time. What is studied is not the event itself, but information that has survived from earlier conditions and remains accessible in the present. This distinction is essential. In cosmology, observation always occurs in the present. Instruments detect signals that arrive now, regardless of when they were produced. These signals carry information about earlier states of the universe, but only if that information was able to persist and travel forward through time without being destroyed. Observation, therefore, is not simply about looking farther away or measuring more precisely. It depends on whether information from a given era can still exist at all. This immediately reframes the problem of the beginning. If information from the earliest moments did not survive, then no future improvement in technology can retrieve it. The limitation would not be one of resolution or sensitivity, but of physical possibility. Observation would fail not because instruments are insufficient, but because there is nothing left to observe. Cosmology has always operated within this constraint, even when it is not explicitly stated. Every successful reconstruction of cosmic history relies on signals that have endured long enough to reach us. Light, released under specific conditions. Radiation decoupled at particular stages. Patterns preserved in the large-scale distribution of matter. None of these are direct views of the past. They are surviving records. Understanding this changes the meaning of progress in cosmology. Progress does not consist of seeing further back in time in a literal sense. It consists of extracting more information from signals that already exist. Improved instruments allow measurements to become more precise, uncertainties to shrink, and competing explanations to be tested. But all of this work remains confined to the domain of information that survived the early universe. The past itself is not continuously accessible. This is where everyday intuition often fails. In ordinary experience, looking farther usually reveals more. A more powerful telescope shows objects that were previously invisible. A more sensitive detector reveals weaker signals. It is natural to assume that the same logic applies indefinitely, that with sufficient advancement, any earlier state of the universe could eventually be observed. Cosmology shows that this assumption has limits. Observation is not guaranteed by distance alone. It is constrained by whether the universe at a given time allowed information to persist. If physical conditions prevented signals from surviving, then observation ends there, regardless of how advanced measurement becomes. The universe can have a well-defined history without that history being fully observable. The existence of an event does not imply the existence of evidence. Cosmology deals exclusively with the latter. To make this clear, it is useful to separate two concepts that are often treated as identical: what happened and what can be known. What happened includes all physical processes that occurred since the universe began. What can be known includes only those processes that left behind information capable of reaching the present. Observation operates entirely within the second category. This distinction explains how cosmology can be both remarkably successful and fundamentally limited at the same time. On one hand, the field has reconstructed a detailed and consistent account of the universe across vast stretches of time. On the other hand, it encounters a sharp boundary that cannot be crossed, not because of missing ingenuity, but because information ceases to exist beyond a certain point. At this stage, it is important to emphasize what this boundary is not. It is not a statement about ignorance. It is not a claim that science has failed or stopped progressing. It is not a suggestion that the early universe is inaccessible due to insufficient effort. Instead, it is a consequence of the physical requirement that information must survive in order to be observed. Once this requirement is accepted, the logic becomes unavoidable. If observation depends on surviving information, then the earliest observable moment of the universe is not defined by time alone. It is defined by the conditions under which information first became capable of persisting. Everything earlier than that moment may have occurred, but it left no retrievable record. This is why cosmology does not attempt to observe the absolute beginning directly. Instead, it identifies the earliest accessible phase and reconstructs history forward from there. The next step, then, is to examine what kinds of information the universe actually provides. What signals have survived? Why did they survive? And under what conditions do they fail? Answering these questions requires moving from definition to evidence. It requires analyzing the specific signals that allow cosmic history to be reconstructed, and understanding why those signals only exist after a certain point. That analysis begins by treating signals not as images of the past, but as the only witnesses that remain. Once observation is understood as the study of surviving information, the structure of cosmology becomes clearer. The universe does not provide direct access to past events. it provides signals. Everything that is known about cosmic history comes from analyzing which signals still exist and what they reveal about the conditions under which they were produced. These signals fall into a small number of categories, but together they form a remarkably consistent record. Light is one of the most familiar. Radiation is another. The large-scale distribution of matter is a third. None of these are the events themselves. They are consequences of events, preserved long enough to reach the present. This distinction is critical. An event can occur without leaving behind any observable trace. Evidence, by contrast, must persist. Cosmology is concerned only with evidence. It reconstructs history by studying the information that survived, not by attempting to access the past directly. Light is often the first example considered because it travels at a finite speed and carries information across vast distances. When light reaches an instrument today, it does not represent the present state of its source. It represents the conditions at the moment it was emitted. In this way, light functions as a record, but only light that was able to travel freely and persist without being destroyed can serve this role. Radiation operates in a similar way. Certain forms of radiation were produced under specific physical conditions in the early universe. If that radiation decoupled from matter and was able to propagate forward through time, it remains observable today. If it could not, then no record remains. The distribution of matter provides a different kind of signal. Matter does not travel across the universe in the same way light does, but its large-scale arrangement preserves information about earlier processes. Patterns in matter distribution reflect the conditions under which structures formed. These patterns persist because matter itself persists. Together, these signals allow cosmology to reconstruct a timeline. Each category of evidence corresponds to a range of conditions under which information could survive. Where conditions allowed persistence, history remains accessible. Where they did not, history disappears from observation. This framework explains both the strength and the limitations of cosmological knowledge. The strength comes from consistency. Independent signals, governed by different physical processes, converge on the same historical account. Light-based observations, radiation measurements, and matter distributions do not contradict one another. Instead, they reinforce a single coherent timeline. This convergence is not assumed. It is tested continuously as measurements improve. The limitations arise from the same source. If an event occurred under conditions that prevented information from surviving, then no category of signal can provide access to it. There is no alternative channel through which the past can be recovered. The absence of evidence in this context is not a gap waiting to be filled. It is the expected outcome of physical conditions that erase information. Understanding this prevents a common misunderstanding. Cosmology does not claim that every past event is observable. It claims that every observable event must have left behind surviving evidence. These are not equivalent statements. The first would imply completeness. The second implies selectivity. This selectivity is not arbitrary. It is determined entirely by physical conditions. When the universe allowed information to persist, history became accessible. When it did not, history ended from the perspective of observation. The success of cosmology lies in how effectively it has used this limited archive. Across most of cosmic history, the surviving signals are abundant and consistent. They allow precise reconstruction of large-scale evolution. They support detailed models that can be tested and refined. The fact that these reconstructions work across independent lines of evidence is not incidental. It reflects the reliability of the signal-based method. This reliability builds confidence, but it also carries an implication that is often overlooked. If the method works so well, then its failure at earlier times cannot be dismissed as accidental. If multiple independent signals all terminate at the same point, the conclusion is unavoidable. Beyond that point, no information survived. This is why cosmology treats signals as the only witnesses of the past. There are no hidden observers. There is no alternate record. If a signal does not exist, the past it would have described cannot be reconstructed. At this stage, it becomes possible to see why the paradox introduced earlier is not a flaw in reasoning, but a direct outcome of the method itself. The universe is observable only insofar as it allowed itself to be recorded. The next step is to apply this understanding systematically. If signals are the only witnesses, then cosmic history must be reconstructed by following those signals backward in time, stage by stage, until they disappear. This backward journey does not begin at the beginning. It begins in the present and proceeds only as far as evidence allows. Understanding how this reconstruction unfolds and where it stops requires examining the universe chronologically, moving from accessible history toward the earliest observable phase. That journey begins by stepping backward through time, guided entirely by the signals that remain. With the role of signals clearly defined, cosmology approaches the past in a specific and disciplined way. It does not begin at the beginning. It begins in the present, where observation is possible, and moves backward only as far as surviving evidence allows. This backward reconstruction is not a guesswork process. It follows a strict sequence. Each step is anchored to signals that can be measured, tested, and cross-checked. The past is not inferred all at once. It is assembled layer by layer, with each layer supported by information that still exists. The present universe provides the starting point. the distribution of galaxies, the large-scale structure of matter, and the measurable expansion all serve as immediate evidence. These observations establish the current state of the universe and define the direction of reconstruction. From here, cosmology proceeds backward by asking a controlled question. What prior conditions must have existed for the present signals to appear as they do? Moving backward in time does not mean reversing physical processes. It means identifying earlier states that are consistent with the signals observed today. This approach ensures continuity. Each reconstructed stage must connect logically to the next, without contradiction. As the reconstruction moves into earlier epochs, the universe becomes simpler in structure, but more extreme in condition. Matter becomes more uniformly distributed. Temperatures increase. Densities rise. Yet, at each stage, signals remain available. Light emitted during later periods continues to arrive. Radiation produced under earlier conditions remains detectable. Matter distributions preserve information about earlier fluctuations. At this point, the method remains reliable. Each reconstructed phase is supported by multiple forms of evidence. Measurements align with predictions. Independent observations agree. Adjustments refine details, but do not alter the overall structure of the timeline. The narrative remains stable because it is constrained by data. This stability is not assumed. It is earned through consistency. When cosmology reconstructs a particular stage of the universe, it does so because the signals demand it. If the signals change, the reconstruction must change with them. This discipline prevents speculation from replacing evidence. It ensures that confidence grows only where justification exists. As the backward journey continues, the universe approaches conditions where radiation and matter interact more intensely. Yet even here, observation remains possible. Signals may become more indirect, but they are still present. The evidence becomes more compressed, but it does not disappear. This is an important point in the emotional arc of the narrative. Up to this stage, the viewer is meant to feel oriented. The method works. The history unfolds in a controlled way. Each step backward deepens understanding without undermining confidence. The universe, while extreme, remains accessible to observation. This sense of mastery is not accidental. It mirrors the actual experience of cosmological reconstruction. For most of the universe's history, the signal-based method is effective. It provides a coherent account that can be tested and refined. The backward reconstruction also reveals a key structural feature of cosmology. The past does not fade gradually into uncertainty. Instead, it remains sharply defined for a long time. Signals do not weaken randomly. They persist reliably across vast spans of time. This persistence reinforces the assumption that observation can continue indefinitely. If signals have survived from such early epochs, it seems reasonable to expect that they might survive from even earlier ones. The method has worked so well that its limits are not immediately visible. The backward journey feels smooth and continuous. However, this smoothness is deceptive. As reconstruction approaches earlier and earlier conditions, subtle changes begin to appear. The signals that once provided clear information start to become less direct. The physical conditions required for information to survive become more restrictive. The margin for persistence narrows. At this stage, nothing has failed yet. The timeline remains consistent. Predictions remain testable. Evidence still exists, but the nature of that evidence begins to shift. The signals that once carried detailed information now carry broader constraints. They still support reconstruction, but with less flexibility. This transition is not a collapse. It is a warning. It indicates that observation depends increasingly on specific physical conditions. It shows that information survival is not guaranteed indefinitely. The method is still functioning, but the requirements for its success are becoming more stringent. This is where the backward journey approaches a critical threshold. Beyond this point, reconstruction will no longer be supported by the same abundance of signals. The universe will enter conditions where information cannot persist in the same way. Observation will begin to fail, not abruptly, but inevitably. The importance of this moment lies in its inevitability. Nothing in the method changes. The same logic applies. The same principles govern reconstruction. What changes are the conditions of the universe itself. The signals that made history accessible begin to weaken. Not because observation is flawed, but because the universe no longer preserves information. This realization sets the stage for the next phase of the narrative. The backward journey has worked precisely as intended. It has delivered a stable, coherent account of cosmic history. It has earned trust. And now, that trust allows a more difficult conclusion to emerge. To understand where and why observation fails, it is necessary to examine how the early universe increasingly prevents information from surviving. That examination begins by confronting the growing opacity of the universe itself. As the reconstruction moves further backward in time, a gradual but critical change begins to appear. The universe does not simply become younger. It becomes increasingly hostile to the survival of information. Up to this point, signals have remained available. They have allowed earlier conditions to be inferred with confidence. But this reliability depends on a specific requirement. Information must be able to travel freely and persist long enough to reach the present. As the universe approaches its earlier states, that requirement becomes harder to satisfy. The reason lies in the physical conditions of the early universe. Earlier epochs were characterized by much higher temperatures and densities. Matter and radiation interacted more frequently. Energy levels were extreme. Under these conditions, information did not propagate in the same way it does in the later universe. Signals that would otherwise travel freely were repeatedly disrupted. This is a fundamental shift. Observation does not fail because signals become too weak to detect. It fails because signals cannot exist independently long enough to carry information forward. The difference matters. A weak signal can be amplified. A distorted signal can sometimes be corrected. A signal that cannot persist at all leaves nothing to observe. As the backward journey continues, the universe approaches conditions where interactions dominate over propagation. Particles collide constantly. Radiation is absorbed and re-emitted repeatedly. Any information carried by a signal is quickly erased by subsequent interactions. At this stage, it becomes clear that transparency is not a permanent feature of the universe. It is a condition that emerged only after specific physical thresholds were crossed. Before those thresholds, the universe did not allow information to move freely across large distances. This increasing opacity marks a turning point in the reconstruction. Earlier, signals do not gradually fade into noise. Instead, they reach a point where they are no longer able to survive. Information does not weaken continuously. It stops abruptly once the conditions required for persistence are no longer met. This challenges a common intuition. In everyday experience, limits are often gradual. Visibility decreases with distance. Clarity diminishes with interference. It is natural to assume that the same pattern applies to cosmic history. That the early universe simply becomes harder to observe the further back one goes. Cosmology shows that this intuition is incomplete. The limitation is not one of degree, but of kind. The issue is not that observation becomes increasingly difficult. It is that observation becomes physically impossible once certain conditions are reached. At this point in the narrative, the backward reconstruction still appears coherent. The timeline has not yet broken. Evidence still exists, but the margin for information survival has narrowed dramatically. Signals that once carried detailed records now only provide broad constraints. This narrowing creates unease for a reason. It suggests that the ability to observe the past depends on a fragile balance of conditions. Once that balance is lost, no amount of observational improvement can recover what is missing. The universe itself determines what can and cannot be known. This is why the emerging limitation cannot be attributed to observational weakness. It is not a failure of instruments. It is not a consequence of insufficient sensitivity. The limitation arises from the physical state of the universe at earlier times. The same methods continue to be applied. The same logic governs reconstruction. Yet the results change because the universe changes. As conditions grow more extreme, the pathways that once allowed information to travel begin to close. Signals are no longer free to propagate. Records are no longer preserved. The universe becomes opaque to its own history. This opacity is not uniform. It increases steadily as one moves backward in time. Each earlier stage restricts information more tightly than the last. The conditions required for transparency retreat until they disappear altogether. At this stage, the reconstruction approaches a critical threshold. Beyond this threshold, information cannot survive in any usable form. Signals cannot persist long enough to reach later epochs. The universe no longer produces records that can be observed. The significance of this moment lies in its inevitability. Nothing in the method has failed. No assumption has been violated. The same signal-based logic that enabled reconstruction now reveals its own limit. The universe does not gradually hide its earliest history. It prevents that history from being recorded in the first place. This realization prepares the ground for what comes next. If information survival becomes impossible beyond a certain point, then the backward journey does not end because of uncertainty. It ends because observation itself reaches a boundary. A boundary defined not by technology, but by physical conditions. Understanding where that boundary lies and why it cannot be crossed requires moving from increasing opacity to complete informational closure. As the backward reconstruction approaches the earliest observable phases, the nature of the problem changes. The question is no longer whether observation is difficult. It becomes whether observation is possible at all. This distinction is crucial. Difficult observation implies that information exists but is hard to extract. Signals may be weak, indirect, or buried in noise, but they are still present. With sufficient improvement, they can, in principle, be recovered. Impossible observation implies something fundamentally different. The information does not exist in a retrievable form. There's nothing to recover. The early universe approaches this second condition. To understand why, it is necessary to examine what happens to information under extreme physical conditions. Information, in this context, is not abstract. It is carried by physical signals. Those signals must maintain identifiable properties long enough to move forward in time. If they cannot, information is lost immediately. Earlier cosmic conditions prevent this in several ways, all of which reinforce one another. At sufficiently high temperatures and densities, interactions dominate over propagation. Particles collide continuously. Radiation is absorbed and re-emitted without maintaining a stable record of its origin. Under such conditions, any attempt by information to persist is overwhelmed by constant disruption. This means that signals are not merely altered, they are erased. A signal that cannot maintain its identity beyond a brief interval does not function as a record. Even if it exists momentarily, it leaves no lasting trace. Observation depends on persistence, not momentary existence. This is where the intuition of gradual loss breaks down. One might expect that earlier signals simply become more distorted, or that some partial information might still survive. But the physical conditions do not allow for partial survival. Information is either preserved long enough to travel, or it is eliminated almost immediately. There is no intermediate state in which degraded information remains usable. This applies to all known forms of information. Light cannot propagate freely. Radiation cannot decouple and travel independently. Matter cannot preserve stable patterns. Any potential record is destroyed as quickly as it forms. The environment does not allow information to separate from the processes that generate it. As a result, there is no hidden channel through which the past can be accessed. This point eliminates a common misconception. One might imagine that even if direct observation fails, indirect methods could still recover earlier information. That correlations, secondary effects, or subtle imprints might bypass the main limitation. But indirect observation still requires surviving information. If no signal persists, there is nothing to correlate, nothing to imprint, and nothing to infer from. The absence is complete. This is why the observational boundary cannot be treated as a technical challenge. There is no improvement in sensitivity that can retrieve information that never survived. There is no clever reconstruction that can recover records that were never preserved. The closure is absolute. At this stage in the narrative, the viewer should feel a tightening of logical constraints. Every possible route for accessing earlier information has been examined. Each one fails for the same reason. The universe, under its earliest conditions, did not permit information to escape. This conclusion does not arise from a single argument. It arises from convergence. Different physical considerations all lead to the same result. High interaction rates erase signal identity. Extreme densities prevent free propagation. Continuous reprocessing destroys records before they can persist. These are not speculative claims. They are consequences of the same physical principles that govern later, observable epochs. The reliability of the conclusion lies in its consistency. If even one form of information could survive, cosmology would attempt to use it. The fact that no such form exists is not an oversight. It is a result. This realization transforms the nature of the boundary. The boundary is not a place where data runs out. It is a place where information cannot exist in an observable form. Observation does not fade. It terminates. At this point, there are no remaining alternatives to consider. The universe does not hide its earliest history behind complexity. It removes the possibility of recording it altogether. This is why the limitation cannot be postponed. It cannot be overcome with time. It cannot be solved by future instruments. It is built into the earliest conditions themselves. Understanding this leads directly to a final recognition. If information cannot survive beyond a certain point, then the boundary encountered by observation is not provisional. It is permanent. It does not shift as knowledge advances. It does not retreat as methods improve. It defines the limit of what observation can ever reach. The next step is to confront that implication directly. What does it mean for cosmology to encounter a boundary that does not move? How does a science proceed when explanation reaches a fixed endpoint? Not because of ignorance, but because of physical necessity. That realization completes this part and leads directly to the conclusion that the observational limit is not a challenge to overcome, but a defining feature of cosmic knowledge. The journey began with a question about the beginning of the universe. That question remains, but it no longer means what it once did. At first, it appeared to ask for a missing piece of history, an event waiting to be uncovered, a moment that lay just beyond current reach. After everything that has been examined, the question changes. It is no longer simply about what happened at the beginning. It becomes a question about what observation can establish, and where its reach necessarily ends. About why some aspects of the universe can be reconstructed in detail, while others cannot be accessed at all. Seen this way, the absence of direct knowledge about the absolute beginning is not a gap to be filled. It is a condition to be understood. Inquiry does not end when observation stops. It changes. When observation is possible, inquiry focuses on reconstruction, measurement, and testing. It refines descriptions and improves precision. When observation reaches a boundary, inquiry shifts toward interpretation. It asks what that boundary implies about physical conditions, about information, and about the structure of explanation itself. This shift does not diminish the role of curiosity. It gives it direction. Curiosity, guided by clear limits, remains productive. It seeks understanding rather than completion. It focuses on relationships, constraints, and consequences rather than inaccessible events. The permanent boundary encountered in cosmology serves this guiding role. It does not block inquiry. It shapes it. By defining where reliable description ends, it clarifies where interpretation must begin. It tells us not what cannot be thought about, but what cannot be claimed as observational knowledge. This distinction matters. It allows scientific inquiry to proceed without overreach. It prevents the confusion of speculation with explanation. It keeps attention focused on what evidence supports, while still allowing reflection on what lies beyond evidence. In this way, the boundary becomes part of the structure of understanding. Cosmology does not move forward by denying its limits. It moves forward by incorporating them, by treating the boundary not as an obstacle, but as information in its own right. Information about the conditions under which the universe allows itself to be observed. The history that can be reconstructed stands on its own, complete within its domain. The absence of access to the absolute beginning does not diminish that history. It frames it. What remains is not a demand for answers that cannot be given, but an awareness of scope. The universe is not fully accessible to observation, yet it is deeply intelligible where observation applies. Explanation reaches far, but not everywhere. And that balance defines how inquiry continues. The original question, revisited with this understanding, no longer asks for resolution. It asks for clarity. Not clarity about the beginning itself, but clarity about how knowledge works in a universe with limits, about what it means to explain, to observe, and to understand. This is not an ending marked by closure. It is an ending marked by readiness. Readiness to continue examining what can be known. Readiness to reflect on what cannot. Readiness to ask questions that respect the conditions under which answers are possible. The universe does not offer complete access to its origin. What it offers instead is something more precise, a history that can be understood deeply, and limits that can be understood clearly. And within those limits, inquiry remains open. Reaching the end of what can be known does not require disappointment. It requires clarity. The realization that the universe's observable history ends before its absolute beginning can feel unsettling at first. But this ending does not undo what has been learned. It does not weaken the reconstruction that came before it. On the contrary, it confirms its reliability. Everything established within the accessible domain remains intact. The boundary encountered does not invalidate the accuracy of past explanations. It does not cast doubt on the consistency of the reconstructed timeline. The signals that support that history remain observable. The evidence remains testable. The conclusions drawn from it remain justified. What changes is not the value of what is known, but the expectation of what knowledge must include. It is important to distinguish between two different kinds of unanswered questions. Some questions remain open because work is incomplete. Data may be limited. Measurements may lack precision. Models may require refinement. These questions remain open because further observation is possible. Progress can be made. Other questions remain unanswered for a different reason. They lie beyond the conditions that allow observation to function at all. No amount of additional data can address them, because no data exists to be collected. These questions are not unresolved. they are inaccessible. The boundary separating these two categories is not arbitrary. It is defined by physical conditions. Recognizing this distinction is not an admission of failure. It is a mark of understanding. It reflects a clear grasp of what observation can and cannot support. Scientific strength does not come from insisting that every question must yield an answer. It comes from knowing which questions can be addressed by evidence and which cannot. Confusing these categories weakens explanation. Separating them strengthens it. The universe makes this separation unavoidable. Its earliest conditions did not preserve information in a form that could survive to later times. As a result, some questions about the absolute beginning cannot be answered through observation. This does not make those questions meaningless. It places them outside the domain of empirical reconstruction. Accepting this boundary does not diminish curiosity. It disciplines it. Curiosity, guided by evidence, remains productive. Curiosity detached from evidence leads elsewhere. Science advances by maintaining that distinction. Within the observable domain, explanation remains robust. The universe's evolution can be described with depth and coherence. Relationships between different epochs can be traced. Predictions can be tested. Understanding continues to grow. None of this is compromised by the existence of a boundary. In fact, the boundary protects this understanding. It prevents explanations from extending beyond what evidence can support. It ensures that claims remain anchored to observation rather than speculation. By defining where reliable description ends, it preserves the integrity of what lies within. This is why accepting the boundary is not an act of resignation. It is an acknowledgement of the conditions under which knowledge is possible. It reflects respect for evidence rather than surrender to uncertainty. At this stage, the emotional tone settles. The earlier tension fades, replaced by composure. The universe's history does not feel incomplete in a problematic sense. It feels complete within its proper scope. The absence of access to the absolute beginning no longer appears as a flaw. It appears as a consequence of physical reality. This shift allows reflection to replace pursuit. Instead of pressing forward in search of extension, attention turns to interpretation, to what the existence of such limits reveals about the universe, to how scientific inquiry adapts when explanation reaches a natural endpoint. The acceptance of limits does not halt inquiry, it reshapes it. Understanding no longer depends on pushing beyond the boundary. It depends on working carefully within it and on interpreting what the boundary itself implies. This perspective stabilizes the narrative. The journey does not end in frustration. It ends in balance. Knowledge stands where evidence supports it. Questions remain where evidence cannot reach. With this balance established, there is room to consider what comes next. not in terms of recovering what cannot be observed, but in terms of how science continues to function when its limits are clearly defined. The universe's history, as far as observation allows, has been reconstructed with depth, consistency, and precision. Across immense spans of time, physical conditions have been traced backward, connected stage by stage through surviving evidence. The account is not fragmentary. It is not uncertain. It is deeply understood within its accessible domain, and yet it does not extend to the beginning. This realization does not weaken the reconstruction. It clarifies its meaning. Understanding does not require total access. Explanation does not depend on completeness. A history can be coherent, predictive, and reliable without including every event that occurred. The universe demonstrates this distinction with unusual clarity. What has been achieved is not a partial story waiting to be finished. It is a complete description of everything that can be supported by observation. The fact that it ends does not make it provisional. It makes it bounded. This boundary marks the separation between what can be established through evidence and what cannot. On one side lies a history reconstructed through signals that survived. On the other lies a region where no observational record exists. The absence of description beyond that point does not indicate confusion. It indicates the end of empirical access. Recognizing this requires restraint. There is a strong impulse to push beyond the limit, to search for answers where observation no longer applies. That impulse reflects curiosity, but curiosity alone does not produce knowledge. Knowledge requires constraint. It requires a clear understanding of where evidence applies and where it does not. The universe enforces that distinction. Its earliest conditions do not preserve information in a form that can be recovered. No amount of refinement changes this fact. The history that can be known is therefore not the full history that occurred, but the full history that remains observable. Accepting this reshapes the emotional landscape of the inquiry. The earlier expectation of total reconstruction gives way to a quieter understanding. The universe does not withhold its origin out of mystery or complexity. It withholds it because the conditions required for observation did not exist. The absence of resolution is not a failure of explanation. It is the outcome of explanation applied consistently. This perspective resolves the tension introduced by the abrupt halt of the narrative. The stopping point no longer feels like an interruption. It feels like a conclusion defined by necessity. The history does not trail off into speculation. It ends cleanly at the point where evidence ends. Within that boundary, the universe is intelligible. Beyond it, description loses its grounding. This separation allows the reconstructed history to stand with confidence. It prevents overreach. It ensures that claims remain anchored to what can be supported. In doing so, it preserves the integrity of explanation rather than diminishing it. The journey, then, does not conclude with an answer to the question of the absolute beginning. It concludes with a clearer understanding of what questions observation can address, and which ones lie beyond its reach. That distinction is not a limitation imposed from outside. It is a feature of the universe itself. This is why the absence of resolution does not signal the end of inquiry. Instead, it marks a transition. The focus shifts from extending the timeline further back to understanding the meaning of the boundary that has been reached. From attempting to observe what cannot be observed to interpreting what the existence of such limits reveals about nature. The universe's history can be known in depth without being fully accessible. Explanation can be complete within its domain without being total. That realization is not a disappointment. It is a form of clarity. It represents the point at which the search for answers gives way to an understanding of scope, where confidence is no longer measured by how far explanation extends, but by how precisely its limits are defined. With that understanding in place, the inquiry does not stop. It changes. What follows is not an attempt to recover what cannot be observed, but a reflection on how science proceeds when explanation reaches its natural endpoint, how questions evolve, and how understanding continues within clearly defined bounds. At this point, it is tempting to interpret the stopping point as an unfinished task, a place where work remains to be done, a problem waiting for better data, better tools, or a better theory. That interpretation is understandable, but it is incorrect. The boundary encountered in cosmic history does not represent incomplete work. It does not mark a failure of observation. It reflects a limit imposed by physical conditions that no amount of refinement can overcome. This distinction is essential for understanding what the boundary means. In most scientific contexts, limits signal opportunity. When data runs out, new experiments are designed. When resolution is insufficient, instruments improve. When uncertainty remains, models are refined. Progress typically pushes boundaries outward. Here, progress does something different. As measurements improve, the boundary does not move. It becomes more precisely defined. The earliest observable phase is described in greater detail, but no observation extends beyond it. The limit does not retreat. It sharpens. This behavior is not characteristic of an unsolved technical problem. If the boundary were caused by missing data, independent methods would encounter it at different points. If it were caused by insufficient sensitivity, refinement would gradually extend access. Neither occurs. All observational approaches converge on the same endpoint, regardless of how they are improved. This convergence confirms that the boundary is structural, not provisional. It marks the point beyond which reliable description is no longer possible, because information does not survive. The absence of observation beyond this point is not due to lack of effort. It is due to lack of surviving evidence. Understanding this prevents a common misunderstanding. The boundary is not a blank page in an otherwise complete book. It is not a chapter that has yet to be written. It is the edge of the book itself. Beyond that edge, description is no longer constrained by evidence. Claims can still be made, but they are no longer grounded in observation. Cosmology, as a science, does not operate there. This does not diminish what has been achieved. On the contrary, it clarifies the scope of achievement. Within the domain defined by surviving signals, the history of the universe has been reconstructed with remarkable consistency. The boundary ensures that this reconstruction remains reliable by preventing it from extending into regions where evidence cannot support it. In this way, the boundary performs a stabilizing role. It separates explanation from speculation. It distinguishes what can be known from what can be imagined. It defines the domain in which scientific claims retain their meaning. Recognizing this role changes how the end of the timeline is perceived. The stopping point is not an interruption. It is a conclusion. Not a conclusion of the universe's history, but a conclusion of what observation can establish. The history does not become vague or uncertain at this point. It becomes inaccessible. This is why additional data cannot extend the timeline further back. Data only exists where information survived. Beyond the boundary, there is nothing for data to capture, no signal to refine, no measurement to improve. The conditions that would allow information to persist are absent. This makes the boundary fundamentally different from earlier limits that were later overcome. It is not a challenge to be solved. It is a constraint to be acknowledged. This acknowledgement does not close inquiry. It redirects it. Instead of asking how to see beyond the boundary, cosmology asks how to understand what the boundary implies, what it says about the early universe, what it reveals about the relationship between physical conditions and observable information. By defining where reliable description ends, the boundary allows the reconstructed history within that domain to stand on firm ground. The universe's observable past is not diminished by this limit. It is made more precise. Accepting this requires a shift in perspective. It requires letting go of the expectation that every question must eventually yield to observation. It requires recognizing that some questions lie outside the domain of empirical access, not because they are meaningless, but because the universe does not preserve the information needed to answer them. This acceptance is not resignation. It is discipline. It reflects an understanding of what scientific explanation can and cannot do. It respects the conditions under which knowledge is possible. At this stage, the tension introduced by the abrupt halt of the narrative begins to resolve. the boundary is no longer seen as a problem to overcome. It is understood as a defining feature of cosmic knowledge. It marks the limit of observation, not the failure of understanding. With this perspective in place, the narrative no longer presses forward in search of extension. It pauses. What remains is not a new direction to pursue, but a moment to reflect on what has been established, and on what it means for history to be both deeply understood and fundamentally incomplete. That reflection prepares the way for closure, not continuation. Up to this point, the reconstructed history appears continuous and complete. Each earlier stage follows from the one before it. The evidence aligns. The timeline holds together, and then it stops. Not gradually, not ambiguously. At a specific point in the past, the historical account no longer extends further back. Descriptions do not become less detailed. They do not fragment into competing possibilities. They simply end. This stopping point is not defined by uncertainty. It is defined by consistency. No matter which line of evidence is followed, light, radiation, or the distribution of matter, the same limit is reached. Independent observations, governed by different physical processes, all converge on the same earliest accessible phase. None extend beyond it. This convergence is decisive. If the halt appeared in only one form of evidence, it could be attributed to methodological weakness. If different observations ended at different times, the boundary could be treated as provisional. That does not occur. The stopping point is the same across all approaches. This removes a familiar expectation. In many areas of science, apparent limits retreat as methods improve. Better resolution reveals finer structure. Increased sensitivity uncovers weaker signals. It is natural to assume that the same process applies here, that refinement will eventually extend the timeline further back. The evidence does not support that assumption. As measurements have improved, the endpoint has not moved. It has become sharper. The properties of the earliest accessible phase are described with increasing precision, but no observation reaches beyond it. The boundary remains fixed. This stability changes how the history must be interpreted. The narrative does not halt because it becomes speculative. It halts because observation reaches a defined endpoint. There is no transition from knowledge to guesswork. There is a transition from observation to absence. At this point, the difference between refinement and extension becomes clear. Refinement improves understanding within the accessible domain. It does not expand that domain. Better data clarifies what is already observable. It does not reveal new eras beyond the boundary. This realization produces a shift in tone. The earlier sense of mastery is interrupted. The confidence built by consistency now confronts a constraint that consistency itself has revealed. The same agreement that supported the reconstructed history also defines where it must stop. The stopping point is therefore not a failure of explanation. It is an outcome of explanation working as intended. This moment creates tension because it contradicts a deep expectation. If the universe has a beginning, and if the history leading up to it can be reconstructed so successfully, it seems reasonable to expect that the final step backward would be accessible as well. The evidence suggests otherwise. The narrative approaches the earliest phase smoothly, then halts abruptly. There is no gradual fade into uncertainty. There is no competing alternative timeline. There is only a clear, consistent endpoint beyond which no description extends. This is the precise moment where the nature of the problem changes. The question is no longer how to refine the reconstruction. It is why the reconstruction ends where it does. Why this particular point, and not earlier or later? Why all evidence agrees on the same limit? Understanding this requires moving beyond the description of the history itself and examining the conditions under which that history could be recorded. The halt does not occur because the universe becomes too complex to describe. It occurs because the universe reaches a state where information can no longer survive in an observable form. That explanation has not yet been given. What has been established here is the fact of the halt itself. Abrupt, consistent, and unmoved by refinement. The narrative does not trail off, it stops. And once that is recognized, the next step becomes unavoidable. If the timeline ends not because of missing effort, but because of physical necessity, then the reason for that necessity must be examined directly. Taken together, the surviving signals of the universe allow a single, continuous history to be traced with remarkable clarity. Within the limits of observation, this history unfolds in an orderly sequence. It does not appear as a collection of disconnected episodes, but as a progression in which each stage follows necessarily from the one before it. Earlier conditions give rise to later structures, and later observations retain records of earlier states. The story begins with the universe in a state far different from what is seen today. Matter is distributed more uniformly. Temperatures are higher. Densities are greater. Yet even at these early stages, the conditions that shape later evolution are already present. Small differences exist. Over time, those differences grow and organize. As the universe evolves, expansion plays a central role. Distances increase. Overall conditions change. Interactions that were once dominant become less frequent. New forms of structure become possible. These changes are not arbitrary. They follow from the same physical rules applied consistently across time. Radiation carries information from early stages forward. Matter responds to gravity and gradually assembles into larger structures. Over long periods, simple distributions give way to complex arrangements. The large-scale patterns observed today preserve traces of these earlier processes. What is striking about this reconstruction is not only its scope, but its coherence. Each phase fits into a larger framework. There are no abrupt breaks in the sequence, no unexplained reversals. The universe does not appear to reset or restart. Instead, it evolves continuously, with each stage leaving behind information that constrains the next. This continuity allows the history to be followed step by step. Later observations are not interpreted in isolation. They are understood as outcomes of earlier conditions. When the distribution of matter is measured, it reflects how initial differences developed over time. When radiation is detected, it encodes information about the state of the universe at the moment it was released. These signals align because they describe the same unfolding process. As a result, the reconstructed history feels complete within its domain. There is a clear beginning to the accessible timeline. There is a clear sequence of changes, and there is a clear connection between early conditions and present observations. Nothing essential appears to be missing from this account. This sense of completeness is reinforced by the way independent evidence fits together. Light-based observations, radiation measurements, and matter distributions all describe the same evolution. They do not compete for explanatory authority. They support one another. Each adds constraint rather than confusion. Together, they form a unified picture. At this stage, the universe's past appears fully accounted for. The major transitions have been identified. The large-scale structure has been explained. The relationships between different epochs have been established. While details continue to be refined, the overall narrative remains stable. This stability produces a powerful emotional effect. The viewer is invited to feel oriented within cosmic history. The universe no longer appears as an unknowable expanse of disconnected events. It appears as a system with a traceable past, governed by consistent rules, unfolding over immense spans of time. There is a sense that the reconstruction has reached its natural conclusion. The timeline stretches far back. Each step is supported by evidence. Each transition makes sense in light of what came before. The story feels whole, and yet, as the reconstruction is followed further backward, a subtle tension begins to emerge. The history approaches a point where the universe becomes increasingly uniform, increasingly dense, increasingly extreme. The stages grow closer together. The conditions change more rapidly. The signals that once carried detailed information now provide broader constraints. Still, the narrative holds. Even here, the reconstruction remains coherent. The sequence does not fracture. The evidence continues to agree. The universe's evolution appears to approach its earliest phase smoothly, without contradiction. This creates a powerful expectation. If the history has remained continuous for so long, it seems natural to expect that it will continue all the way to the beginning, that the final step backward will simply reveal the first moment. The structure of the narrative encourages this assumption. The accessible history feels complete. The gaps have closed. The evidence aligns. The universe's past appears fully mapped. It is precisely at this point, when the reconstruction feels most secure, that the final limitation becomes unavoidable. The timeline, for all its depth and consistency, does not extend indefinitely. The convergence of evidence does not carry the narrative all the way to an absolute origin. Instead, it brings the reconstruction to a clear and consistent endpoint. The history does not break, it stops, and that stopping point is not accidental. It appears in the same place no matter which evidence is followed. The sense of completeness achieved within the accessible domain now reveals its consequence. The universe's observable history, though vast, still ends before the beginning itself. That realization marks the turning point of understanding. What follows is not a collapse of the narrative, but a recognition of its boundary. The strength of the reconstructed cosmic history does not come from any single observation. It comes from agreement. Different ways of observing the universe rely on different physical processes. They measure different quantities, respond to different conditions, and are subject to different sources of uncertainty. If these independent approaches were pointing toward different histories, confidence would quickly erode. That is not what happens. Instead, they converge. Measurements based on light, radiation, and the distribution of matter all support the same broad sequence of events. Each method operates independently, yet each leads to compatible conclusions about how the universe evolved over time. This convergence is not assumed in advance. It emerges from comparison. Light-based observations reveal how structures change with distance and time. Radiation measurements preserve information from specific early conditions. The large-scale arrangement of matter reflects how small initial difference developed into the structures observed today. These forms of evidence are governed by different physics, but they describe the same history. This agreement is what gives cosmology its authority. When one line of evidence is examined in isolation, it can suggest multiple interpretations. When many independent lines converge, the range of viable explanations narrows. What remains is not a collection of possibilities, but a constrained account. Importantly, this convergence does not depend on accumulating ever more detail. It depends on consistency. The precise values of parameters can change as measurements improve. Uncertainties can shrink. Models can be refined. But the underlying sequence, the order in which major transitions occurred, and the relationships between them remains stable. independent observations continue to reinforce the same structure. This stability is not the result of circular reasoning. Each type of evidence places constraints on the others. Predictions derived from one set of observations must agree with results from another. When they do, confidence increases. When they do not, models must be revised. Over time, this process has reduced disagreement rather than amplified it. As observational techniques have improved, the convergence has become stronger, not weaker. Signals that were once measured crudely are now measured precisely. Where ambiguity existed, constraints have tightened. The overall picture has become clearer. This is why the reconstructed history is treated as reliable. It is not based on a single fragile argument. It is supported by multiple independent confirmations. Removing one line of evidence would weaken detail, but it would not collapse the narrative. The remaining signals would still point in the same direction. This convergence also explains why the history appears so complete. As independent observations continue to agree, the sense emerges that the major elements of the universe's evolution have been identified. There are refinements to be made, but no large gaps where incompatible accounts compete. The structure of the timeline holds. At this stage, the universe's past appears well described within the limits of observation. The evidence does not fragment. It aligns. This alignment produces a subtle but powerful effect. It creates the impression that the reconstruction is approaching closure, that the remaining unknowns concern precision rather than structure, that the broad outline of cosmic history is already in place. This impression is not unreasonable. It is supported by the evidence. And it is precisely this sense of completeness that makes the next realization more significant. Because even as agreement strengthens and the history becomes more coherent, all independent lines of evidence still end at the same point. No method extends beyond it. No signal crosses it. The convergence that builds confidence also defines the limit. Understanding how far this agreement extends and where it stops requires stepping through the reconstructed history itself, examining it as a continuous whole. The existence of a fixed observational boundary does not reduce the scope of what cosmology has achieved. It clarifies it. Once the limits of observation are understood, it becomes possible to define with confidence the domain within which knowledge is reliable. Cosmology does not claim access to every moment of the universe's history. It makes a more precise claim that a vast portion of that history can be reconstructed in detail, supported by evidence that survives to the present. Within this accessible domain, cosmology has achieved a remarkable level of consistency and precision. The reconstruction of cosmic history begins with the universe as it is observed today. Measurements of expansion, the distribution of matter, and large-scale structure establish a well-defined starting point. From there, earlier conditions are inferred by following surviving signals backward through time, step by step. This reconstruction does not rely on a single type of evidence. It depends on multiple categories of information, each governed by different physical processes. Light that reaches us today carries records of earlier states. Radiation preserves information from specific transitions. The distribution of matter reflects conditions under which structures formed. All of these signals converge on the same historical sequence. The strength of this approach lies in its coherence. Each reconstructed stage is physically connected to the next. Later, conditions follow necessarily from earlier ones. Predictions derived from one part of the timeline can be tested against evidence from another. When discrepancies appear, they lead to refinement rather than collapse. The overall structure remains stable because it is constrained by observation. This stability justifies confidence in the reconstructed history. The account that emerges is not a loose outline filled with uncertainty. It is a continuous narrative supported by evidence across vast stretches of cosmic time. While details continue to improve, the sequence itself remains intact. Independent measurements repeatedly reinforce the same conclusions. Crucially, this confidence does not depend on ignoring the limits of observation. Recognizing where observation ends strengthens the reconstruction rather than weakening it. It prevents overextension. It ensures that explanations remain grounded in evidence. By accepting the boundary imposed by physical conditions, cosmology avoids confusing speculation with knowledge. Within those limits, the history that can be described is extensive. It includes the evolution of large-scale structure, the changing distribution of matter, and the conditions under which radiation became able to travel freely. These stages are not isolated facts. They form a connected sequence that can be traced backward with consistency and precision. This reconstructed history is not static. As measurements improve, parameters become more accurate and uncertainties shrink. Yet the overall narrative does not shift because it is anchored in signals that persist. The key point is this: limitation does not imply fragmentation. The fact that observation ends at a specific boundary does not mean that the history leading up to that boundary is incomplete or unreliable. It means that the portion of history within reach can be treated as a coherent whole. What follows is therefore not a speculative account of what might have happened. It is the most complete reconstruction that evidence allows. Only after this history is examined in full does a deeper implication emerge. The universe's history, as far as observation permits, is remarkably complete. And yet, even this complete account does not extend to the absolute beginning. The timeline, for all its depth and consistency, still ends early, By this point, the logic of the reconstruction has closed in on a single conclusion. The limitation encountered in the early universe is not accidental, and it is not temporary. It follows directly from the conditions required for observation itself. Everything established so far leads to this outcome. Observation depends on surviving information. Information depends on physical signals. Those signals must be able to persist and travel forward through time. When the universe no longer allows that persistence, observation necessarily ends. This chain does not contain a weak link. As a result, the observational boundary does not shift with technological progress. Improving instruments does not change the physical conditions under which information either survives or fails to survive. Better detectors can measure existing signals with greater precision, but they cannot create signals that never existed. This distinction is essential. In many sciences, better data extends reach. In cosmology, better data clarifies limits. The same improvements that refine measurements also sharpen the point at which observation stops. The boundary becomes more precisely defined, not more distant. This effect has already been observed. As measurements have improved, the earliest accessible moment of cosmic history has not moved earlier. Instead, its properties have become clearer. The signals marking that boundary have been studied in increasing detail. Their consistency across independent observations has reinforced the conclusion that they represent the earliest observable phase. This consistency is not a coincidence. It reflects the structural nature of the boundary. If the limitation were technical, different observational methods would encounter different endpoints. If it were provisional, improved data would gradually extend access. Neither occurs. All signal-based approaches converge on the same stopping point. This convergence confirms that the boundary is not a problem awaiting solution. It is a feature of the universe's early conditions. At this stage, the emotional tone of the narrative shifts. The earlier sense of mastery does not collapse, but it is tempered. The universe remains understandable across vast spans of time. Its evolution can be reconstructed with precision. The success of the method remains intact. What changes is the expectation of completeness. Cosmic history can be extensive without being total. It can be coherent without being exhaustive. The existence of a limit does not undermine what is known. It defines what knowing can mean. This acceptance is not a retreat. It is an adjustment. Rather than framing the boundary as a failure of explanation, cosmology recognizes it as a consequence of explanation's own requirements. The same physical principles that allow reconstruction also impose a stopping point. This realization resolves the tension introduced at the beginning of the
To
narrative.
listen to extended episodes
The paradox
without ads
is
or
no longer
interruption,
puzzling.
join our premium
It is
subscription
understood.
on Apple Podcasts.
The universe has a history that can be studied in detail, and yet that history begins earlier than observation can ever reach. Both statements can be true at the same time. The boundary once identified becomes a reference point rather than an obstacle. It marks the transition between what can be supported by evidence and what cannot. It separates reconstruction from speculation. It defines the domain within which scientific explanation remains grounded. All necessary concepts have been established. Observation has been defined. Signals have been identified. The reasons for their disappearance have been explained. The permanence of the boundary has been demonstrated. What remains is not to push further back, but to take stock of what has been reconstructed. The next stage of the narrative does exactly that. It presents the full known history of the universe in a structured, comprehensive way, beginning from the present and extending backward to the observational boundary. Only then does it become possible to see the final implication clearly, that even the most complete cosmic history still ends before the beginning